Hello everyone, welcome to my channel. I am Ritika and today we are going to solve the LeetCode daily problem minimum cost path with edge reversals. So let's quickly understand what the problem state. You are given a directed weighted graph with n nodes labeled from 0 to n minus 1 and an array edges where edges I equal to ui, vi, wi represents a directed edge from node ui to node vi with cost wi. Each node ui has a switch that can be used at most once. When you arrive at UI and have not yet used its switch, you may activate it on one of its incoming edges VI to UI, reverse that edge to UI to VI and immediately traverse it. The reversal is only valid for that single move and using a reversed edge cost 2 into WI. Return the minimum total cost to travel from node 0 to node n minus 1. If it is not possible, return minus 1. So basically we are given a directed weighted graph having n nodes. The numbering starts from 0 to n minus 1. Also, we are given an array edges that consist of three types of value ui, vi and wi, where ui and vi represent the node of the graph where they have a directed edge from node ui to node vi with the edge cost of wi. Now we have to return the minimum total cost to travel from node 0 to node n minus 1, while we have to maintain one more point that is given in the problem, that is each node UI has a switch that can be used at most once. But what the switch do? That is, whenever we arrive to a node that, for example, UI, and if the switch of node UI has not been used till now, then we can activate it for to reversing one of its incoming edge. That is, if there is an incoming edge VI to UI, then we can reverse it to UI to VI, and immediately we can traverse through it and we can reach from UI to VI. Now, the reversal process makes the edge cost twice of the previous one. That means if the previous edge cost is WI, then the edge cost now will be 2 into WI. And using this, we have to return the minimum total cost to travel from node 0 to node n minus 1. If it is not possible to find the minimum total cost, then we will simply return minus 1. Now, for example, we have n equal to 4. That means the nodes are numbering from 0 to n minus 1, that is 0 to 3. Now, edges consist of 0 to 1. That means we have a directed edge from node 0 to node 1 with a edge of 3. Similarly, 3 to 1 with the edge of 1. 2 to 3 with the edge of 4, with the cost of 4. It is also cost of 1. And here 0 to 2. And the cost will be 2. So if we use the path 0 to 1, the cost will be 3. Now we have reached to node 1 and the cost is now 3. Now we have a edge that is 3 to 1. If we use the switch of node 1 and we can reverse the incoming edge, the edge will be now 1 to 3. But the cost will be also changed to 2 into 1, that is 2. But ultimately we have reached the n minus 1 node. So the total cost is 3 plus 2, that is 5. That will be the minimum possible total cost to reach to travel from node 0 to node n minus 1. Similarly, we have another example n equal to 4. That means it has also the nodes from 0 to 3 and the edges is 0 to 2 and with a cost of 1, 2 to 1 with a cost of 1, 1 to 3 with a cost of 1 and 2 to 3 having a cost of 3. Now, is there any, do you need any reversal in this example? No, because we have already edges from 0 to 2. So, we can move to the node 2. Here, we have a edge between 2 to 1. So, ultimately, we reach the node 1. And from 1, we have a direct edge to 3. So, we can ultimately reach to the n minus 1 node, while we have the minimum possible total cost, that is 1 plus 1 plus 1, that is 3. Now coming to the constant, we have n in between 2 to 5 into 10 to the power 4, its length in between 1 to 10 to the power 5. Its size already we know, it consists of ui, vi and wi. Ui and vi in between 0 to n minus 1 because they represent the node. Wi in between 1 to 1000. Now coming to the solution approach, here we have to find the minimum total cost. Now whenever we try to find any minimum total cost or minimal minimum total edge cost, something like that, which algorithm comes to our mind first? Dijkstra algorithm, right? So here also we can use the same algorithm to find the minimum total cost to travel from node 0 to node n minus 1. But as we have the cases to reverse the node, and the cost will be also changed, so that things also we have to keep in mind. So what we can do is, in the case of Dijkstra algorithm, we just add or store the edge cost of the outgoing edges, but here also we will calculate the possible incoming edges cost as well. For better understanding, let's quickly go through the Python code as well. So as discussed in the approach, we will keep track of the forward edge and the backward edge, that is the incoming edges and outgoing edges. Both the cases will be implement in the Dijkstra algorithm. That is, first of all, we are initialize two adjacent matches, that is adjacent out and adjacent in. Adjacent out for the outgoing edges and adjacent in for the incoming edges. Now we will traversing through the edges array, that is for u, v and w, and we are just appending the values. For out cases, we are using the node u and adding the neighborest the neighbor node with the edge cost. Similarly in the adjacent in. Now we have initialized the distance array that has a length of n, and initially we are storing float infinity for everyone, because whenever we will find a minimum cost or the a cost lesser than float infinity, we will update this. Now this 0 equal to 0, because at node 0 we do not need any additional cost, so we will just represent this 0 equal to 0. Now q, that will be used in our Dijkstra algorithm. Now heap q, we are using the heap here, and pushing the or adding the node 0 along with the current weight, because the current we don't have any weight or the edge cost initially, so we are just adding 0 comma 0, and we will go through the queue each time. Now first we will pop the element from the queue. If the weight is not equal to list of node, then we will simply skip it and go to the next node. If the node is next iteration, if the current node that we have popped is equal to n minus 1, then we will simply return the weight, because we have reached the ultimate final node. Now first we are using the forward edges, that is for neighbor and neighbor weight in adjacent out of node, the new weight will be weight with the neighbor weight. If the new weight is lesser than the weight stored in distinct array, then we will update it. Along with this, we will also add it to the heap queue. But here also we have to consider the reverse edge cases. So in that case, we have used the adjacent in, and just one more chance, we have to make it twice of the neighbor weight. Remain things will be same as the forward cases, and thus we will calculate or find the minimal total cost. If there will be no such cost we have find, then we will simply return -1. So now run the code. Yeah, it's running. Now submit. Yeah, so our code is running good. If you like the video and approach, please do like, share and subscribe our channel, and follow for more such content. Thank you.